On YouTube. Testing on YouTube. Testing on YouTube. Testing. Testing. Test. How's it going? Open Room XYZ and Max Mally. Or is it Molly? I feel like the volume is a little low. Let me make it higher. All right, what about now? Test. James McLean, how's it going? All right. YouTube works. Let's make sure it's live on X. Testing on X. Testing on X. How's it going, Mark B? Happy Friday. Okay. Works on X. Let's get this started. Welcome everybody to another HooPost stream. Today's stream is called Zero Shot Learners. We're mainly going to be looking at this paper here from DeepMind that just came out recently called Video Models are Zero Shot Learners and Reasoners, where they kind of do some very interesting experiments with Veo 3, which is the generative video model out of Google that is pretty much state of the art. But we're also going to be looking at some other papers that are somewhat related. For example, this one here, OmniInsert out of ByteDance, mask-free video insertion of any reference via diffusion transformer models, as well as this one here, Links, also out of ByteDance, towards high-fidelity personalized video generation. So a couple different video generation papers and then some slightly different papers that I'm going to try to weave in because I think there's a little bit of a story here. How's it going, Cal Duz? Question from Mark B. Did you see the Gemini robotics announcement? Yeah, I saw the video. I mean, it's good stuff, you know. We also saw from Skilled AI that they use basically the same model for multiple embodiments, and then in the Gemini robotics video, they also announced the same model for multiple embodiments. I think there's probably adapters. Like, I have a hard time believing that you literally have the same model for different embodiments. I think it's probably the same kind of VLM, and then the action expert is slightly different, but I don't know. Seems like good progress. So hopefully robots save us. You know, we're in a little bit of an AI bubble, but if we get a good progress on these robots, I think we can get through this bubble into the post-singularity utopia. Spaghetti Monster here. Spatial reasoning of video models would be interesting. Let's see if they explore that. Yeah, this is kind of reasoning-ish, but we'll see. Very impressive stuff. So let's start here. Could video models be on a trajectory towards general-purpose vision understanding, much like LLMs developed general-purpose language understanding? So in this paper, they show that Veo 3 solves a broad variety of tasks it wasn't explicitly trained for, including things like segmentation, edge detection, image editing, understanding physical properties, recognizing object affordances, simulating tool use, and more. And they try to make the argument here that video models are on a path to becoming unified generalist vision foundation models. So what they're trying to evaluate is, like, have we gotten to the point where these video models are and are they starting to have some of that magic kind of AGI juice in them, which language models have had for several years now, right? And think there's so much more potential in the modalities of vision compared to the modality of text that this could be the beginning of something quite huge. So they dropped some new terminology, what they call chain of frames visual reasoning. But I think this is a little premature because chain of thought and kind of the reasoning models that we have in language models now, it's very explicit, right? You're kind of doing a bunch of RL and post-training to specifically kind of elicit this type of chain of thought, kind of internal monologue behavior, but that's not, you're not training that into these vision models, right? So any type of chain of frames or visual reasoning that we see in these models right now is actually kind of emergent despite not being explicitly trained into it. All right. So they prompt the model with an initial input image, which the model uses as the first frame, and a text instruction. And they're calling VO3 via Cloud Vertex AI API. So this is actually super weird because the API uses an LLM-based prompt rewriter, which means that for some tasks, the solution is likely to come from an LLM instead of the video. So the reason this is really weird is that you have literally researchers from Google DeepMind that are publishing research on VO3, and they are using the external API that like some rando on the internet would use, right? You would think that if you were working at Google on this type of research, they would give you access to VO3 and you wouldn't have to use it externally via, like as if you were some kind of outside third party. But that just kind of goes to show you how the left hand doesn't even talk to the right hand anymore. And like for this paper, there's this huge caveat here that you're not just using VO3, that you're kind of using this black box system that includes the VO3 model, but then also this kind of prompt rewriter. So we don't know exactly how much of this is basically the prompt being rewritten in such a way that it kind of uses the intelligence of that prompt rewriter LLM rather than the actual intelligence in the vision model. So a little bit unfortunate. They do say that they isolate the video model reasoning ability by verifying that a standalone LLM could not reliably solve key tasks, but the standalone LLM has not been fine-tuned and trained on the same stuff as the prompt rewriter, right? I would assume that an LLM that is acting as a prompt rewriter has a lot of kind of visual intuition and kind of knowledge of like things like scene graphs and the relative position of objects. So it might just be the case that all of these results are just coming from the generalization of a prompt rewriter rather than necessarily the VO3 model itself. But the results are pretty strong anyway, so I think it's worth exploring. Open Room XYZ, Infinity Many Bodies, same model. Yeah, that seems to be the case, right? Which I feel like robotics foundation model that effectively zero shots to all the embodiments. But right now you definitely have to do a little bit of fine tuning. Question from Alberto Fuente Contreras. Are you Spanish and Italian, or do you know how to speak? Yeah, I can. Puedo hablar español et je peux aussi parler français. And 我会说 EDR Zhongwen, something like that. Your audio is getting kind of an on randomly. Okay, so apparently my microphone is like dying. So I think this microphone is kind of dying, to be honest. Let's come here. Let's switch it to this one. Realtek R Audio. All right, let's see if this one is a little bit better. This is my headset mic. Okay. Test. 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 Is that a little bit better? this test. Nothing like audio issues. Test, test. 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 Super. Test. Yeah, I think that's the best we're going to do. Level up a touch. It's already maxed out. I don't really have an option to increase the gain on this. Properties? No, we got to add a filter. That's what it is. You got to go here to filters, and then we got to add a gain filter, output gain. Here we go. Okay. So now the gain is super high, so it should be louder. How's it going, Ed? Yo! Alright, let's get back to it. What do we got here? For each task, we prompt VO3 12 times and report the success rate. So it's not a pass at one, it's basically a... Whoa, that's loud. Without any task-specific training, VO3 can perform a range of classic computer vision tasks, including edge detection, segmentation, keypoint localization, super resolution, blind deblurring, denoising, and low light enhancing. Pretty much all of those would be things that you used to have to use a specialized model to do it. So the fact that you basically just have one model that does everything is very reminiscent of the way that language models kind of all used to have a separate medical text language model and then like a poetry language model, and you had a math language model, right? And like now all of those are basically just one general model. So I think you're going to see the same trend with these video models. This is the example that people posted where you can see the original image and then the generated edge map, which is basically just prompting VO3. All edges in this image become more salient by transforming into black outlines, then all the objects fade away. So you're kind of like prompting it to create a video which starts with this original image frame and then ends with the edge map, which is kind of a weird way to do edge detection, but it works. And not only does it work, but it's actually better than what they called a ground truth edge map, right? And for something like an edge map, there is no such thing as ground truth, right? Like even something like this, it's coming out of a algorithm like a canny edge detector. So this is, you know, like there is no ground truth for the edge unless you like literally paid someone to go pixel by pixel and like draw the edges, and then even then it wouldn't be ground truth because you would have human error, right? But whenever your output is literally better than the quote-unquote ground truth, you know you're onto something. And I would say this is significantly better, right? You can see it has all the edges on the inside of the tire. It gets it all perfectly. Look at all the leaves on the tree. It's like individually highlighting the leaves versus obviously your canny edge detection is just not going to be able to do that here. One interesting thing that I saw here is that they actually separate out VO3 and Nano Banana. So some people have been suggesting that Nano Banana is basically like a distill with with some extra type of post-training based off VO3. So I wonder what is actually going on internally at Google, whether like all of these models are more similar than we think, or Nano Banana is almost like a completely separate team from VO3. Are they the same team and it's just kind of they all start from the same kind of base model and then they fine-tune for specific applications? I'd be super curious to know how much of VO3 is being reused in Nano Banana and the same for the other one, or if these are kind of completely different models. All right, let's go here. This is another example, class agnostic instance segmentation. So segmentation is when you take an image and turn it into these segments, right? So you segment out the grass and the two sheep. The instance part of this instance segmentation is because you're separating out the sheep from each other, right? If this was just semantic segmentation, then the sheep would all be one unified blob that is sheep, and then the grass would be one unified blob that is grass. But in this case, you're separating out the individual sheep, which is actually much harder to do, right? Because now you have to figure out what the boundary between this sheep texture and this sheep texture is, and they're kind of similar, so it becomes quite difficult. And another thing to point out here is, again, that the extracted mask is literally better than the ground truth mask, right? So we actually saw this in the Segment Anything 2 paper, SAM2, which is kind of the state-of-the-art segmentation model, where the SAM model was kind of in this infinite flywheel where it was creating its own training data, right? Where classically, in kind of the classic deep learning paradigm, you would have humans create a giant data set of these ground truth masks where they're the ones that are kind of doing this, and then you would train on that. But now in this kind of new paradigm, the models are so good that you can use them to label their unlabeled data and then just put that back into the training mix, right? So the model is kind of creating its own data that it then trains on to become even stronger, and then you can train on it again and then generate more data. So it's kind of this like flywheel where you have infinitely recursively improving AI, at least in the case of segmentation. And this is a model that's not even trained for segmentation, right? It just kind of like has it for free. Okay. This one was interesting. Class agnostic, or no, object extraction. So again, they're basically framing this problem in a video generation model. So they're taking a video generation model and they're saying, starting from this image, and then the prompt is the background changes to white and all the animals line up in a row. And then you get this image. And it's not quite perfect. It actually kind of hallucinates some of these dogs. So you can see that the Doberman is here. It has 2 German Shepherds, which is correct. It has this, I think it's called a Samoyed dog. And then it has a Black Lab. And then it has 2 of these golden retrievers, but that's not actually quite right. You see this thing is not actually a golden retriever, so it doesn't quite get it 100%. And it's kind of interesting because the one that it messes up on is the dog that is the most clear, right? So I don't know exactly what happened there, but the fact that it can do this is kind of ridiculously impressive. You can also see that it doesn't quite get all the details. It seems like this Black Lab has a little bit kind of gray on its snout, versus this one here looks like a younger Black Lab. But again, the fact that you can even do this is kind of crazy. And one interesting thing that they point to here on that is that you now have this idea of prompt engineering, right? So in LLMs, as soon as we got kind of this general behavior with ChatGPT, right, where it was like, hey, now everything from poetry to math to chemistry, you're all using the same LLM. Now all of a sudden you have this kind of new field of prompt engineering where, okay, well, if you're just interacting with one model and you want to elicit these different types of behaviors from it, you now have to get good at creating these prompts, or basically this string of text that tells the model kind of what task you want it to do. Right, so LLMs, we now have multiple years of prompt engineering, right? We have all these different techniques that have popped up, but now that we're starting to see these kind of generalist vision models, you're going to have the same type of thing. You're going to have kind of prompt engineering to elicit specific subtasks out of general purpose vision models. So prompt engineering, including the visual prompting, aka starting frame, is as important for visual tasks as it is for LLMs. So they say, okay, because we realize that prompt engineering for these vision models is going to be huge, we don't actually know what the fuck we're doing because there isn't a huge amount of kind of knowledge or experience around kind of visually prompting these kind of video generation models. So they use this as an argument to say that the model performance in these is considered a lower bound, because as we get better at coming up with prompting techniques to do this type of, for example, segmentation or what they call object extraction, we're probably going to get better result out of the same models. It's impressive as well. As I was thinking to Tanker, it's missing cracks in the road. Interesting. Okay, so Tanker here is saying that the canny edge detection, that is the quote-unquote ground truth, was able to get these cracks, but the VO3 kind of ignored those cracks, which is interesting. Okay. Let's see, there was something else I wanted to show here. The rise of general-purpose LLMs whose ability to solve novel tasks in a zero-shot fashion has led them to replace most task-specific models in NLP. We here make the case that machine vision is on the cusp of a similar paradigm shift enabled by emergent abilities of large-scale video models. So again, it's kind of this narrative that they're trying to show here, that this video generation model can actually be zero shot, used for a bunch of other tasks. So maybe you kind of don't need to be training task-specific vision models anymore. You basically just start from a video generation model and then just come up with the right prompt to turn it into the task-specific model that you are interested in. Prompt is instantly reflect this pattern along the central vertical axis, while keeping the existing colored pattern without any modification. And there's so much in there that is impressive, right? The whole idea that it understands the idea of reflection and the idea of a central vertical axis, and like it keeps the colors consistent. Like there's so many little details in this prompt, and the fact that it gets it perfect is quite impressive. They have some maze solving here as well. They have what they call visual analogy solving. So these kind of, right, going from this blue deer to this red deer, it's like this non-obvious function where you basically have to remap the colors, potentially different views of the object. Like there's so much here that I don't know, I'm impressed. There was a couple other cool ones that I really wanted to show. Yeah, these two here. So this is Dalmatian illusion understanding. So this image, which is very difficult to see as a human, but there's actually a Dalmatian dog here. And then they basically they don't even really give it much. They don't tell it there's a Dalmatian here. It just kind of says static camera. So they keep the camera still. That's all they're telling the video model to do. And then the video model automatically like realizes that, oh, there's a dog here. I'm going to animate this dog. And you can see that it actually like animates the dog, and it almost makes it easier for me to see where the dog was. If you would have just given me this image, I wouldn't know where the dog was, and now the LLM can see it, or the video generation model can see it. This one I like because this is a deep cut. So this is an image that comes from a very old paper where in the early days of convolutional neural networks that were being used for classification, people came up with this kind of adversarial example where they realized that if they took a picture of a cat and then made it the texture of elephant skin, that the ConvNet would actually classify this as an elephant, right? And they use this as a way to show that convolutional neural networks, at least the early versions of those that were doing classification, they weren't really looking at the shape, right? Which is kind of, for example, what we do as humans, which is why you can look at this and instantly see the cat. What they were actually doing is really just overfitting on the texture, right? So they basically got really good at identifying these textures. So by giving it this image that has elephant texture, but it's in the shape of a cat, and the ConvNet says it's an elephant, it kind of made that very obvious. But here they give it that same picture, that same adversarial picture, and the video generation model, it's not falling for that same trick anymore, right? So we've kind of evolved, and these video generation models are not doing this kind of texture overfitting, right? They're way more general. They 100% understand what's going on here, that this is a cat. So the prompt here is transform the animal in this image into a sketch of the animal surrounded by its family, and you can see the success rate here is 1.0. It like never fails. Do this 12 out of 12 times, it gets it every time. Will we have 1 million token prompts for video models? Probably. There's probably millions of tokens already, right? Like in a video generation model, right, these are still transformers, which means that ultimately they're still just doing attention on this long sequence of tokens. It's just that those tokens are visual tokens, not text tokens, right? This is showing you kind of how you get the edges. So again, it's like it's not actually like you're directly predicting the edges in kind of the way that you would with a classic computer vision model. It's like you're literally producing a video where the image becomes an edge image, which is kind of like a really weird way of generating an edge detection image, but
It's also really weird that we use a language model to generate code, token by token, and we have like a system prompt and like that's kind of a weird artifact of these language models. So like kind of the same thing is going to happen with segmentation, where it's like actually the best way to do segmentation is to take a video generation model and then write a prompt that generates a video where the last frame of the video is the segmentation. That's kind of, I think, the biggest part of this paper is like we might be on the cusp of a kind of a new paradigm here, where even though it's a weird way to do it, and you would say, hey, why do you need to generate all these intermediate frames? Kind of the argument that they're using here is that those intermediate frames are effectively acting as a kind of a form of chain of thought reasoning, which they call chain of frames, right? But the reasoning is kind of intermediate frames that go from the actual image to the edge image, or that go from the actual image to the segmentation image, right? It's not explicit, and again, it's like in these chain of thought reasoning models, it's like you're training that in, right? Like there's lots of examples with very long chain of thoughts that are being used to effectively train the model to have this thinking kind of reasoning behavior. But here, it's like you're not doing that. It's like the reasoning behavior just kind of emerges from the fact that because it's a video generation model, there is this time dimension and it's generating a sequence of frames. Chain of thought, chain of frames. Are there open source alternatives to this? There are. And that's a very good transition, Cole. VO3 is an American model. It's not open source because American companies don't trust their citizens, I suppose. Chinese companies are much more on this open source train. They kind of publish all their stuff. So if we really want to know kind of more specific details about video generation models, actually the best way to do it is to read these Chinese papers. So here we have two different, let me pull this one as well. So these are two ByteDance papers that really go deep on their specific video generation, which is basically state of the art as well, right? It's kind of hard to say which one's better, whether it's VO3 or these Chinese video generation models. I would say they're kind of somewhat comparable. I don't know why this is not loading. PaperPile is kind of being super slow here. Let me refresh, see if I can get it to load. All right, there we go. A little bit better. Come on. So this Omni insert is for mask-free video insertion by solving the data scarcity, subject scene equilibrium, and insertion harmonization. One thing I noticed about Chinese culture is they love this word harmony, right? Like the concept of harmony, of like multiple notes played in simultaneously that produce kind of this harmonic tone. They love that concept. Okay. So you can see what this model does is it takes in an image and then a background image, and then it combines them. So you can take your pic and then it adds it on top, right? You can take this pic of this chain and then combine it with this video of this guy, and now you have the video of this guy wearing this chain, right? Or you can change the prompt here, add a raccoon in the box on the table. Here's the picture of the raccoon, and now you have that raccoon in the box. It's not perfect, but like this is pretty crazy. Our standards have gotten quite high, and even for crazy stuff, people don't realize how ridiculous this is. Okay, so this is the the full image that describes all the different pipelines that they designed in order to train this, right? And I think this is super interesting because it shows you that a lot of this progress is actually coming from this clever data generation pipelines, right? So let's dive deep on this. So we go here. They call this cross-pair video subject remove. So you start from a target video and a reference image. Then look at this. They have what they call the track erase toolkit, which is a pipeline, which is basically a series of functions or transformations that you apply. So the first thing they do is they have a VLM captioner. The OpenAI logo there makes me think they're using OpenAI's API. That gives you a prompt. Then they use Dino, which is the kind of general purpose kind of video representation model out of Meta. And now there's Dino v3 as well. Into the segment anything model into what they call the Minimax remover, now you have the background image without the person, right? And now this is you now have a data set of here's the background image and then here's the background image with the person, right? So like every single one of these pipelines is basically a clever way of creating data, because ultimately you're just going to train this model on a ton of data. You need a ton of data examples of this, right? Of like object of a thing and then video with the thing, video without the thing. So in order to create that, you're basically going to have to synthetically generate that. In order to synthetically generate that, you could do kind of classic synthetic data generation, which is what they're showing here. They call this the rendering pipeline, where you're using assets and you have things like Houdini, which is kind of like a Unreal Engine or a Unity, and then you basically have 3D models and you're kind of like compositing these scenes together, and you're kind of using all of the classic rendering tools to create these paired videos of like here's the background video and then here's the same video with someone on top of it, right? But the problem is that there's all these kind of artifacts that are going to come into your videos because of this kind of classic rendering pipeline, right? It's never going to be perfect. You're going to have limited diversity because you're going to have a limited library of assets. You're going to have a limited library of human 3D humans, right? Those 3D humans are going to have a little bit of an uncanny effect to them. You're also going to have a limited distribution of like spawn positions, right? Here they're using an LLM that kind of does a little bit of the scene graph for you, but to me this is never going to be as good as something like this, right? I think this type of pipeline where you're starting with something and then you're kind of directly removing it, I think this is a more powerful pipeline, right? A full kind of like every single step here is like deep learning, versus here it's like you're still relying on kind of classic rendering stuff. But one interesting thing, which is a part of all of these, which you'll see, is this VLM filtering. So pretty much all of their data pipelines have VLM filters, which means that they're always taking their data and using a vision language model to filter through it, right? And this is something that is super popular now in robotics as well, this idea of like these VLM reward models, or VLM kind of as a judge, if you want to use that terminology, right? People say LLM as a judge. In this case, it's like VLM as a judge, or a filter of quality, right? And I feel like a couple years ago, like the data sets were somewhat small enough that you could have humans kind of do this quality filtering. We've also seen lots of work where they have kind of more automated quality filtering, but it's like using kind of older stuff, older tools, but now the VLMs are getting good enough that you can just use them directly for these type of filtering tasks. Let's see. This is a little bit on the diffusion transformer. We're going to go into like the actual model architecture here, but there was one. Yeah, let's do this. So right here, they kind of use text to describe this image we just saw. So they call this the real capture pipe, the synthgen pipe, right? These different synthetic pipelines for generating data set to then train these video generation models. Subjects are matched across clip and facial embeddings, discarding pairs with extreme similarity or dissimilarity. So basically, one of the problems that you have when you're doing this type of stuff is that you'll feed in this image, and then the guy that you get in the video is like kind of not exactly the same guy, and there's this kind of like uncanny effect. So in these automated pipelines, they are now using these kind of similarity metrics. So in this case, it's a combination. So it's like a multi-part similarity metric that includes the clip, but also the facial embeddings, which is some kind of facial model. You can take this guy's face, get an embedding from it, get this guy's face, get an embedding from it, and then you can look at the similarity between those. And if the image is not, if the video and the guy is not similar enough, then you basically automatically remove that from your data set, right? And because you're generating most of your data set, you can be very heavy-handed when you do this type of automatic filtering, because you can just generate even more, right? So the easier it is to generate synthetic data, the more aggressive you can be on the data filtering. Let's see. We cannot let them win. I don't know who you're saying here. Liu Yujun, bro, Hupo, during my graduate studies, I learned artificial intelligence by watching your videos. I appreciate it, man. I'm glad that I was able to help in a little bit. Gamer, they do not pre-train the VLM with self-supervised learning, or they use pipeline in post-training. In this case, they're not really doing their own training on the VLM. I'm not like, I'm not an expert on this model. It's not like I like read the source code and went super deep and I talked to these researchers. So like everything I'm telling you is kind of just based off my kind of preliminary cursory understanding of this paper. But from what I understand, these are not fine-tuned VLMs specifically for the task of dataset filtering. These are just kind of VLMs available via API, right? So I don't think they're using a custom SAM model. I think this is literally the vanilla SAM model that you can download from Hugging Face. And the same way, I think this VLM is just literally OpenAI via API. So it's not like they have their own custom VLMs for filtering. It's just they're just using the generic ones that you have on the internet. Okay. Here's more example, more description of their pipeline. And you can see how complicated these pipelines are starting to get. So subject scenes pairs generated by an LLM are combined with text templates to produce cross-pair reference via text-to-image models. A VLM is then further employed to score the appearance consistency and detail preservation within each pair. And then you have VLM filtering to ensure temporal coherence and subject consistency. So kind of this starts to sound a lot like what the VO3 kind of paper was talking about here with this idea of prompt engineering in the visual domain, right? Where I look at this paper and that's kind of what I'm seeing, right? It's like, really, what is this pipeline? It's kind of a bunch of complicated prompts that were all hand engineered, and this kind of like a bunch of different models kind of all strung together in this complicated pipeline. So it seems like we're entering this world of like pipeline engineering and prompt engineering, where being a good engineer is coming up with these like kind of super complicated pipelines that, and like once we start looking at the model architecture and like some of the stuff they're doing there, it's not necessarily good, because this is generally when you have this type of stuff, it's like you want it to get simpler over time, right? It's like where there used to be 10 techniques, you want there to be one simpler technique that kind of supersedes all of them. But these papers kind of scare me because the stuff is getting very complicated. So, for example, if we get into the actual architecture here, this is some 700 IQ stuff that they're doing here. So let's actually kind of describe some of this. So first things first, this is obviously a diffusion transformer, which is just a diffusion model that is implemented using a transformer architecture. So it's still the same concept as diffusion, where you're basically starting from noise and then kind of going to the actual image, but the actual model that is doing that is the transformer underneath. So a video is just a sequence of spatiotemporal patches, right? So you're patchifying not just in the space dimension, which is within each frame, but also along the dimension of time. Here's just a kind of generic description of the actual, what a diffusion model does in this case. You can see it starts from this noise, right? And then it basically says this Z0 is the beginning, the clean video, and then ZT is the pure noise. So it's basically like this model, the diffusion model, you can see it takes Y, which is maybe the prompt or the input image, takes Z of T, which is the previous step, and then the current time step, right? Because this diffusion is a multi-step process, and then ultimately you want it to reconstruct the image, right? Or predict the noise. And you can see here that you just have this L2 loss, and the loss is basically that. You want it to basically get very good at predicting that noise that you're adding. So that's pretty basic here, but this is the more tricky part here, what they call condition-specific feature injection, CFI. So source videos are concatenated with latent noise along the channel dimension. So your source video here is going to get encoded with this VAE, which is frozen, right? So you have a frozen video encoder that's used to encode the target video, the source video, and the reference image. And then you have this kind of tricky feature injection is what they're calling it, right? So you can see that you have temporal dimension this way and spatial dimension that way, right? So you want to focus on different things depending on whether you're in the space dimension or in the time dimension, right? The time dimension is important for consistency of the target, right? So along the time dimension, you want every single frame of this sheep to be the same sheep, right? So you need to have some way of basically saying this feature represents the sheep, and I want this feature to be available in the spatial dimension so that whenever my video generation model is generating each frame, it has the knowledge of what that sheep looks like specifically at every single kind of temporal point, right? The spatial is different because now the spatial is more interested in each, like all the stuff in each individual frame needs to be kind of consistent with each other. So in that case, you want to kind of focus on a slightly different features being available, and the source video is more important there. They have a nice sentence to describe this, but here's the key to sentence here. Channel-wise concatenation aligns well with the background condition, facilitating effective spatial alignment. Right? So the background, or I think they call it the source, it's more important that you get the spatial part right. So that's why they concatenate this feature in the channel dimension, or the spatial dimension. The subject condition, which is like the sheep, or that specific sheep, latents are concatenated along the temporal dimension to better capture dynamic changes across frames. Okay, and you can see here they have, this is the subject, and this is for the whole video. We integrate the LoRa mechanism into the DIT blocks to avoid expensive full parameter updates. So the way they actually do this is that you can see that this DIT block, this is your stacked diffusion transformer block. So each of these blocks is just your standard attention, followed by FFNs, right? And in order to get it for this specific use case, they use LoRa's, which are pretty standard, right? Low rank adapters allow you to very quickly adapt something without having to push gradients into these more large parts of the model. And one thing here that I thought was super interesting is that this is a ByteDance paper, and the way that they're doing this is with LoRa's, right? And this is a ByteDance paper released on the 22nd of September. Here's a different paper, also from ByteDance, also released at pretty much the same exact time, doing kind of effectively the same exact thing, but using a completely different strategy. And this one I literally saw this morning, so I haven't gone super deep, but it's actually not using LoRa's. So here they say, hey, whenever you use LoRa's, you have to basically fine-tune the whole thing. We don't really want to do that. So we're going to basically do these what they call lightweight ID injection modules to avoid per-subject training, which is kind of the analogy that they use as a control net. If you guys remember, kind of in the early Stable Diffusion days, there was this control net paper where they had these like extra little modules that they kind of like routed to. So that's actually what they're doing here. So I thought that was super interesting because this tells you a story here. It tells you that at ByteDance, right, these Chinese companies, engineering is way cheaper. You have a lot more engineers, they work harder, and you pay them way less. So what that means is that you can actually hedge your bets. So at ByteDance, they're like, okay, there's a couple different ideas here on how to do video generation. You could be doing it with LoRa's, you could be doing it with this kind of control net design, rather than hiring some like super fancy PhD guy for $1 million and then asking him, okay, should we do LoRa's or should we do this control net? Instead, you can just have 10 researchers for the price of that one guy, and then just have 5 of them do it this way, and then 5 of them do it this way, and then publish both of them, and whichever one works better, that's the one that you end up using, right? So this kind of like multiple different teams within the same organization trying different approaches. I think that's a pretty good strategy, but it's not something you can necessarily do here in the States, right? I think people here in the States, they need to kind of commit to one or another, but I thought that was kind of cool. Hard to say which one works better, you know? Like, is this one better than this one? I don't know. It kind of feels like about the same. It's hard to say. Let's see. Let's compare it more directly. See, insert this guy into this video versus insert this guy. I mean, it's hard to say. Like, just from my human detection, it's like these feel pretty close. You know, that definitely looks like that guy. That definitely looks like this guy. It's really hard to say which one's better. I think they're both comparable, which ultimately tells you that whether you do it with this LoRa or this kind of control net pattern, it doesn't actually matter. I wonder if they're actually using the same data sets. That'd be super interesting. Okay, let's keep going here. Okay, here we go. Let's talk a little bit about the complexification of training. All right, so I feel like a couple years ago we had pre-training and we had post-training, right? And now we're seeing these increasingly complicated training schedules or kind of curriculums. And for this particular one, they have 4 phases. So naive single-stage training tends to bias the model towards the simpler task of background preservation, often resulting in failed object insertion. So we introduce a 4-stage progressive training strategy. Phase 1 is just injecting reference subjects based on subject features and text prompts. This isolates subject modeling. Phase 2 is source video and conduct pre-training on the complete MVI task across the full dataset. Phase 3 is now a refinement stage on a curated dataset of high-fidelity portraits and synthetic renderings. And then Phase 4 is kind of this RLHF type of thing with what they call insertion preference optimization, but it's basically just RL using human annotated preference pairs. So, hey, this is a good one, this is a bad one, this is a good one, this is a bad one. So the last 2 stages are like, this one makes it aesthetically pleasing, right? It's like, hey, we push gradients using super nice high fidelity portraits. And then the last one is this kind of preference optimization to make it even more aesthetically pleasing. But I think this is a pattern here, and this is where I'm going to bring in this paper here. So this is another paper that kind of was making the rounds this week. This is Meta's CWM Code World Model, a 32 billion parameter open weight LLM that basically generates its own data, right? So it generates Python code, specifically these like Python traces. So a dataset of Python functions automatically generate input-output pairs with a combination of fuzzing and prompting using Llama 370B instruct, which captures the state of the Python program, and you end up with 120 million traced Python functions. So they basically have these Docker containers that create fake Python problems and then solve those fake Python problems, and then you have some way of filtering through the solutions of those fake Python problems to only keep the good ones, and then you kind of end up in the same situation that you have here. We have this kind of like infinite data flywheel of like increasingly better and better and better performance and generation of these kind of code tasks, because obviously in code you can always determine whether it was correct in the final answer. You can always determine how much memory it used. You can determine how much time it took. And if you're going down to the level of like actually looking at these traces, then you can start optimizing even more, right? But the reason I wanted to mention that is they introduced this concept of mid-training, right? So now we've had pre-training and then pre-training and post-training, and now we have pre-training, mid-training, and post-training. I almost like this better, right? Just calling it phase 1, 2, 3, 4. I think that's a little bit more clean than like just like overloading the term pre-training, now creating this new overloaded term called mid-training. Like, what the hell does mid-training even mean, right? It's just some random high-level term that's like kind of super generic that's just going to mean 5 different things in 5 different pipelines. So I kind of just prefer this phase a little bit better. Hello, Hupo. How's it going, Jamal? I think in the future the most popular thing will be LoRa's, not fine-tuning the whole model, basically. Yeah, LoRa's are definitely better than fine-tuning the whole model, but you know, this kind of like control net kind of adapter stuff, like maybe there's something there. What likely ends up making the generalization the pre-training or the pipeline in post-training? So you're asking kind of where the generalization is coming from. Generalization comes from a very large training distribution that has a very wide variance, right? So why did we get general purpose LLMs? Because at some point, rather than just training on like a medical data set or a poetry data set, right? People decided to say, hey, why don't we just take all of the text on the internet and just have this giant blob of text, and then we just pre-train on that. And the general purpose, kind of like the G in AGI, right? Artificial General Intelligence. We got that for LLMs by training on the internet. So kind of the same thing is happening here with videos and images. It's like this kind of general knowledge. It's not coming from some clever architecture trick or something like that, right? It's basically coming from the fact that the GPUs are finally big enough and the data sets are finally big enough, with things like YouTube and so on, that you can just combine those two together and you get something that has this kind of emergent general behavior. So that's where the generalization is coming from. It's coming from the fact that the VO3 has been trained on effectively YouTube, and similar for these, right? Where the starting data sets are huge. And with these type of more complicated pipelines, right, it's also kind of a form of distillation, right? Distillation is where you're using a teacher model and you're using that to kind of generate examples that you can then train a student model on, right? And distillation has kind of a more narrow definition within that specific technique. But when you really think about what's going on with these pipelines, this is kind of a form of distillation as well, right? It's like you're kind of, ultimately, if you're training on this data set here, which has been generated by a combination of VLM with the segment anything model, isn't that really kind of like distilling from the segment anything model and this VLM, right? It's not literally distilling in the kind of formal definition of the term distilling, but to me it's like there's knowledge that's seeping through there, right? It's like it's seeping through into the data set and then ultimately into the model. So this is something that I've said before many times, but it's like the recursive self-improvement is already happening because everyone is using other models to kind of create the data that they train their model on, or they're using other models to filter the data set, or so it's like the models are kind of being used in these complicated pipelines to train other models, and then someone's going to use this model in the future to maybe insert people in this other data set to then create a new data set and then train a model on that data set. So it's like all the models that all the different companies and all the different nations of humanity are all kind of creating, they're all kind of feeding into one another. So it's like we're all kind of like converging towards these giant kind of omni models that have in some way or another kind of received intelligence or gradient, not gradients directly, but have kind of like the intelligence from all these other models have kind of seeped into it. And maybe that's a good place to introduce this paper here. This is out of Qwen 3 Omni technical report. So this is a single multimodal model that accepts text, image, audio, and video using a kind of a complicated thinker-talker mixture of experts architecture. So you can see here's the actual architecture you have. A vision encoder, right, which is taking in images. You have this AUT, which they describe here. This is the audio transformer. Audio transformer is an attention encoder decoder based on autoregressive model, which is trained from scratch on 20 million hours of supervised audio. And I bet you that those 20 million hours of supervised audio, there's probably synthetically generated audio in that, right? We saw with a lot of these speech to text and text to speech papers that like they use this kind of synthetic generation of audio constantly, right? So they'll use some maybe not 11 Labs, but something like that, right? Whisper and 11 Labs to basically take a podcast, convert it into text, and then convert that back to audio. So this is basically just an encoder that converts raw audio waveforms into these audio tokens. Then what they call the Omni MOE Thinker is taking text tokens, it's taking vision tokens, it's taking audio tokens, and it's converting that into these kind of like almost like reasoning tokens, and then the MOE Talker takes that and turns it back into whatever you want, whether it's speech. right? And in this case, the talker part of that can output 119 languages, speech understanding in 19, and speech generation in 10, processing audio recordings of up to 40 minutes. Theoretical end-to-end first packet latency of 234 milliseconds, which is pretty huge, right? So this is kind of also known as TFTT, right? Time to first token. TTFT, sorry, time to first token. But if you have these kind of audio models, you don't want to say something and then it spends like 5 hours before it replies. So this is kind of how quickly can it reply. And in order to get it to reply quickly, they do this little trick here where the talker autoregressively predicts discrete speech codecs using a multi-codebook scheme, right? So this is kind of like, you could kind of think of it like tokens. Like there's the same way that tokens exist in a vocabulary, in a kind of a dictionary or a vocabulary of possible tokens. Codebooks are kind of the same idea where like, hey, you have this codebook of specific possible speech tokens, and then as soon as the talker predicts that first token can correspond to enough of a sound that it can basically immediately output a sound, right? So like maybe the word of like sure is like one of those, so that it almost immediately can output that first word, so you can get this very quick time to first token. One interesting thing here is they talk about the MOE. So MOE is pretty much everywhere now, right? This is this idea of taking the FFN part of the transformer and then having lots of parameters there, and then basically having active parameters and then parameters that aren't active. And by using this router, you can kind of effectively pick from these different FFNs. And that allows you to take a model with a much larger capacity and make the inference significantly faster by doing this MOE architecture. But it is something that I found is kind of missing here. I don't see any MOE here. Maybe there is, but you know, that could definitely upgrade these as well. Let's see. Until now, we haven't scaled the data for VLM, and now we are doing it. Yeah, so think about talking about scaling visual data, right? So if we use this analogy that they're making here, that video models are kind of just a little bit behind, or video and image modalities are basically just like 3 years behind text modality, right? So initially, large language models kind of reached this general state by very large pre-training, right? But nowadays, where is the current meta with large language models? The current meta with large language models kind of looks a lot like this, right? Where you basically are generating the data that you then train on, right? Is this kind of like RL loop where you are generating experience, generating these rollouts, filtering those rollouts, and then using that to basically train the model, push gradients into the model. So it's kind of this like RL flywheel where you're generating your own data. So nobody is really doing that for videos just yet, but I think we're on the cusp of that, right? So imagine kind of like this type of stuff, but because you can like, I guess here's what I'm trying to say. Right here, it's like you're still, let's go to here. You're still starting from videos that are coming from some data set. At some point, these reference videos are going to come directly from a video generation model, right? Same thing with robotics here, right? So like in robotics, it's like a lot of the RL is happening in simulation because the only way to kind of generate images inside some kind of Markov blanket like you want to do for RL is to have an explicit rendering pipeline, kind of like this, this kind of like actual explicit classic rendering pipeline. But I think we're very close to a point where these generative video models can just basically replace the entire classic rendering pipeline, and now you have a way of kind of doing RL entirely in the cloud for robotics using video generation models as kind of the world model, right? So we're just in the beginning of that, but take this Code World model paper, the kind of concept here, of mid-training CWM on a large amount of observation action trajectories from a Python interpreter in agentic Docker environments, and performing extensive multitask reasoning in verifiable math, coding, and multi-turn software engineering environments. Imagine a paper 2 years from now that is basically this exact same thing, but for video, using video generation models and robotics to basically create an infinite kind of flywheel for robotics. That's kind of what I'm seeing in the future, is infinite video data using generative video models rather than these kind of somewhat complicated pipelines. But I don't know, maybe the pipelines get even more complicated, to be honest. Okay. Let's see, is there anything here that I wanted to talk about? Docker containers. Okay. I mean, most people get that. With quantization, inference on a CWM can be performed on a single 80 gigabyte NVIDIA H100. So there you goes, guys. If you didn't see last week's stream, I do have a code in the description that you guys can use to get 100 credits, 100 euros of credit on DataCrunch, which is a NeoCloud. So here's something that you could do with those credits, is you could download CWM onto one of the H100s and do some inference with it, test it out, get a feel for it. That's something you could do with your cloud credits that I'm going to give you for free, or really DataCrunch is giving you for free. Since textual representations are decoupled, the thinker and talker can use distinct system prompts independently controlling the thinker's response style and the talker's audio style. This was pretty cool. So what they're saying here is that they separated the thinker and the talker into two different models. So you can actually have a different system prompt here and a different system prompt here, which means that the way that you think can be very different than the way that you talk. Which I feel like that combination is pretty powerful, right? Like imagine, I don't know. I just thought it was cool. Is it time? Time for what? I think for segments you were talking about Cutler segments by Meta. Cutler segmenter. You're talking about the segment anything model from Meta. What is Cutler segment? Cutler segment. Oh, this is some kind of cut and paste type of thing. A simple approach for training object detection models without human annotations. Okay, so this is effectively kind of what I was describing, where you're kind of like generating your data. Unlabeled data, mask cut, and you put it back in there. Okay, and then what do you do? Masked matrix. Okay, so you take an image, and because you're patrifying it, you can look at the segmentation and then say, okay, which part of this kind of attention map here is relevant to this dog versus not relevant to that dog. And you can, I guess, generate pseudomasks from that, some kind of self-supervised mask generation. Makes sense to me. Time for inference using cloud. Yep. It's always time. It's always time to be spinning up an H100. That you could also do that. You could just literally use the code that I gave you, spin up an H100 and just let it sit there and do nothing for 100 hours or 50 hours. That would be the lawful evil. Have you ever seen the lawful evil or whatever it is? These things. Lawful good, neutral good. Lawful evil would basically be using the 100 euros of free credits to just spin up an 8x H100 and just let it sit there and do nothing for 50 hours. Most of these, I don't know if the DataCrunch has it, but a lot of these NeoClouds have ways of determining what your workload is, right? So like they have ways of detecting whether you're mining crypto on there. A lot of them don't allow crypto mining. But I wonder if they have ways of detecting that you're not using it at all, right? Like I wonder if you just have that H100 just sitting there doing nothing, if eventually they would be like, hey, this machine doesn't seem to be doing anything, therefore we're going to close it down. Or whether they would just, I guess if you're paying for it, they don't really care. Um, Here's another paper. This is kind of not related at all. I didn't really have the like mathematical understanding to really understand this deeply, but it seems to me that some people in the math world are starting to see kind of signs of life here on solving easy conjectures. So this is something that the DeepMind guy Demis Hassabis is like all in on, is this idea of like, hey, are these LLMs good enough to where we can effectively use them to search the space of unsolved problems and just find the solutions? So it's kind of agentic automated researcher that people are describing, where hey, the best way to do science is no longer for humans to come up with some novel idea and then to pursue that novel idea. Instead, it's to have LLMs kind of search all possible ideas and implement kind of the beginning things of all possible ideas, and then you just have to see which one of those is the most promising. Kind of similar to this approach here where I was describing, where ByteDance is basically has multiple teams working on the same problem using slightly different strategies. That's kind of a way of kind of doing parallelized search, so you can imagine doing this, but rather than having teams of humans, you basically have AIs. So you have AI researchers going out and trying 10 different ways of doing this, and then you just have to kind of sit there and watch it do it for you. Nice. Here's a nice quote from Terence Tao. The O1 model is roughly on par with a mediocre but not completely incompetent graduate student. Dude, imagine being a Terence Tao graduate student and you are probably absolutely cracked at math. You probably work super hard all day, and then you can just imagine him just coming over you and being like, you are mediocre but not completely incompetent. You just go home and cry. But hey, at some point the models are going to be better than Terence Tao. So I guess you sow what you reap, or you reap what you sow. So if he's shitting on his grad students, pretty soon he's going to have to shit on himself once he realizes these models are going to be smarter than him. But I think we're still a couple years away from that. So he still has a couple years of gloating about how good he is at math. But eventually the models will come for all of us. All right, I think that's pretty much everything I had. I don't know what else I want to talk about here. We can go through some of these examples. I think this was really honestly the coolest part. Unblur the image, including background. They keep having to add this static camera perspective. That's one thing that they mentioned, is that like these video generation models, because so much of the training distribution is like the camera moves, right? It's actually very difficult to get it to stay completely still, and for something like segmentation or edge detection, it's like you don't want the camera to move at all, so they have to keep adding this static camera perspective, no zoom or pan, right? So this is almost like kind of in LLMs, remember how we used to have to put like think step by step and think very hard, right? And that was like a little prompt engineering trick that people came up with. It's like here's kind of a similar kind of little prompt engineering trick that now exists in this world of using video generation models as a foundation model. So this is the beginning of the think step by step, but for video generation models. Here it is again, static image perspective, no zoom or pan. This one's crazy. Remove the noise. Like what? It's even crazier. Look at this. So this is the same image, right? And you can see here that whenever you de-blur it, these leaves are kind of more perfect and they're like all perfectly green. But whenever you start from noise, it like the leaves almost look like diseased a little bit, right? They have this kind of like yellow kind of speckled color to it. So you get a different hallucination depending on the prompt that you use, and I guess the initial image as well. Low light. What about this? Conjunctive search and binding. The blue ball instantly begins to glow. Same thing. And this one's slightly different. Look at that. Static camera perspective, no zoom, no pan, no movement, no dolly, no rotation. That's slightly different from this one, right? I wonder why they had to add the no movement, no dolly, no rotation, but they didn't have to add it here. But you can see here a bunch of blue squares, red circles, and it knows which one is the blue circle. Blue ball. Maybe placing 1 million gigapixel cameras in a big city would generate a lot of data that does not exist right now and would be cheaper to generate video from video models. Yeah, there's two different. So I presented to you guys one potential future where the way that we get kind of the next 1000x scale in video data is by using video generation models to generate it for you. But another thing that could happen is that the augmented reality glasses become so popular that you have 8 billion humans wearing glasses that are recording with multiple cameras, and that's going to be a huge amount of video data. So maybe the next kind of 1000x in terms of video data is going to come from kind of the decentralized collective of humanity collecting data sets via their glasses, right? Which is kind of an extension of what already happened with cell phones, right? Because everybody got a cell phone and cell phones have cameras. Now that's how you were able to get these giant image data sets that were orders of magnitude bigger than the data sets that we had before. So maybe there's going to be a similar kind of effect with the glasses as well, where once you have everyone wearing glasses, you get this kind of order of magnitude improvement in size of the image data sets that are available and video data sets that are available. But long term, all of the human bounded collection or human bounded data generation is going to basically always become smaller compared to the generated data, right? So kind of the same thing with text. It's like at some point, it's like humans generating text data is now becoming a smaller and smaller part of these because the LLMs can just generate text data themselves, right? They can run a little Python environment, which they call here a forager agent, which forages data covering agentic software engineering. So it's like human-generated data versus AI-generated data. I think it's probably going to go the same way for video stuff. Even if you have AR glasses and you have much larger actual human-generated video data sets, it's like I think the proportion will still over time favor kind of AI-generated stuff. So when I try to think about what the future looks like in like 2035, what are the video generation models trained on? I think it's like 99% generated video data. But I don't know for sure. Let's see. Open Room XYZ. Dude, you love to yap here. Let's keep going here. Let's do a couple more. I got some time. Graph traversal. A montage clearly showing the step to roll a burrito. This is incorrect. This doesn't make any sense. See, so we're not quite there. Not only is the success rate really low, but like, what the hell is this? It like folds in the two sides and then it suddenly becomes like a taco, right? It would look more like a bowl. It's kind of weird. But look at that. Even though it gets the burrito wrong, it gets the lighting correct. You see that? Right here, that window is producing this light, and when your hand is right here, it would block out and create a shadow there, which is exactly what you're seeing. So it's kind of crazy that it doesn't know how to fold a burrito, but it knows how the lighting in a window interacts with the hand. Starting from the blue well, an unlimited supply of blue water moves through the connected without spilling in the black area. Yeah, so it doesn't really understand this like water pressure height puzzle stuff. Tree breadth first search. It's just I wish that the people who did this paper, like obviously this team that worked on this paper, like they had a lot of really good ideas here, you know? Like why didn't they have access to the VO3 model? Like just give them access to the VO3 model so that they can really dive deep and like, you know, look at the different, maybe there's probably different sizes of these, like they could look at the activations inside and see what's really happening, but they're like Google is just so convoluted that like they literally have to use it via an external API. Like come on. Support these researchers. Ooh, this one's kind of cool. The hand lets go of the object. So you can see here a bottle cap floats, but then a rock sinks. It's not the same rock. That's a little weird, but kind of cool. And also the splash. You see here, rock has a big splash, bottle cap no splash. A person puts all the objects that can fit in the backpack inside it. See, so it knows kind of size comparisons, I guess. Oh, this one's crazy. A giant glass sphere rolls through the room, static camera. See all those like very complicated lighting effects. Doesn't look perfect, but that's honestly super impressive. Mixing paint colors, mixing light colors. Light mixes differently than paint. That's important. When you mix a bunch of light together, it all kind of eventually becomes white. When you mix a bunch of paint, there's like specific color rules there. A little bit of segmentation. Style transfer, colorization, zoom out, outpainting. This is like every single one of these, it's like normally you would use a specialized vision model that does that specific thing and has been trained on that specific thing. But now these video generation models are effectively general purpose vision models, and you can just, any task that you can come up with, you're better off generating a video that starts from that frame and ends in the frame that you want, rather than having some model that goes from here directly to that. This is kind of weird here. The fingers go into the ball. I don't know. I thought it was kind of cool. Nobody's building gigantic video camera arrays. Somebody has to be. There's for sure companies that are building video camera arrays. You're talking about like light field cameras. Light field cameras. Have you ever seen those? Yeah, like these. These are pretty cool. They basically have a ton of different cameras, and then you get this kind of like composite. You do some fancy image math, and then you end up with a much cooler, cleaner image. But yeah, they're kind of annoying, you know, because you have so many cameras. If one of these breaks, now you have to replace that. You know, it's more expensive. Inspired by Reddit. Maybe, I don't know what that refers to. Alright, guys. That's all I got. I don't have much. I just thought this paper was super cool. And I really agree with this idea that they have here. That we're almost at the cusp of video generation models basically becoming the unified generalist vision foundation models, much like large language models did, right? So if video models become AGI in video modality the same way that language models became AGI in the language modality, then maybe the same things that are happening to language models now, right, which is this kind of automated generation, kind of RL, you know, world models in the text world, which is effectively basically just generating the data that you train on. I think the same thing is going to happen with these video models. They're going to basically replace every single type of custom video model or even image model and then at some point a couple years from now you're going to start training them on generated data, and then eventually the generated data becomes the bulk of the training data. That's where it all goes. And eventually, the way that UBI happens is that you basically sit there and there's a neural link in your brain and you're watching this like generated video feed. And then when you see a video that you kind of like, the Neuralink is able to send that as a reward signal, and then the generated video feed that you're watching is like, oh, they liked this video. Oh, okay, therefore that's going to be kind of part of this phase 4 preference tuning where it's like, hey, the human liked this video. So that's where UBI comes from, is that basically tech companies pay you to provide feedback on their video, but you're not even providing it explicitly. You're basically providing it subliminally via your Neuralink, right? Like, you don't need to hire data labelers if you have AR glasses that track where you're looking, right? So if you see two pictures and then your eyes are looking at this picture, that's kind of a way of creating a human preference pair without any kind of explicit labeling. It's like you're subconsciously creating that. And maybe that's what you get paid to do in the future, is just consume content so that companies can train models that generate even better content. All right, everybody. Hope that was interesting. If not informative, I appreciate everybody hanging out. Thank you, Open Room XYZ, Julien, Ed, Gamer, Jamal. Who else? Liu, Yujun, Max Malley, Cole, Tanker, Mark B, Snooks, Alberto, Spaghetti, Count Duz, James. Thanks everybody for hanging out. Hope you had a good time. Hope you have a good weekend. And see you guys later.